Welcome to this week's Colloquium. This is part of the Distinguished Colloquium series. This is the fourth of 5 throughout the year. We've got one more coming up in April, and that'll be W.E. Murner. And today I have the distinct privilege to introduce Professor Anil Seth, who is a colleague and friend from the University of Utah. So he got his PhD in 2006 from the University of Washington. We'll forgive him for that. He postdoc at the Harvard-Smithsonian Center for Astrophysics for 5 years after that, more or less, and came to the University of Utah in 2011. And I was there at the time, and it was part of what I thought was a unique and very bold move on the part of the department at Utah to hire a bunch of astronomers all at once and suddenly become a Department of Physics and Astronomy. And Anil was part of that effort, part of that sequence of hiring. And I had the pleasure of overlapping with him as a faculty colleague there for 5 years. He's going to talk to us today about black holes, large black holes at the center of small galaxies. And this was something that in 2014 hit the press in a big way. There was lots of major press. He did a BBC interview on this. And just the kind of surprising idea that you find these massive, massive objects in compact dwarf galaxies and things like that. So, without any further ado, I'm going to let Anil take over, and thanks for coming.
Okay, thank you for having me. All right. So yeah, I never managed to make it to Wazoo until now, but I did see your football team a couple times when I was a grad student. Okay, so I'm going to be telling you today about my work on finding black holes in little galaxies. This picture that I'm starting with has like a mystery in it, which will be kind of discussed at greater length later in the talk. So when you see it again, the mystery will be answered. So the work I'm going to be presenting includes a lot of work from my students and postdocs. In particular, I'll be talking about work that my student Yu Nguyen, who is just graduating this year, and my student Chris Ahn have done. Okay, so we're going to start this story at the center of our own galaxy. So this is the roughly central 100 light years or so of our galaxy. And what you can see in the middle there is this bright clump. And that bright clump is actually about 30 million stars packed into the central 10 or 20 light years of our galaxy. And they're all swarming around each other. And we call this thing a nuclear star cluster. And if we zoom into the very center of that, so this is the central 10th of a light year, then we can actually see individual stars moving around and map out their motions. And this is work that Andrea Getz at UCLA has done. And what you're seeing here is the compilation of a whole bunch of 20 years of observations. So this movie wasn't just made by taking a movie camera, it was made by taking sequences of images. And what you can see is that all of the stars, there's several stars here that are actually closed. They've orbited all the way around the little star here at the center. And that star there at the center, there's hardly anything there. There's a weak radio source, and otherwise it's an unnotable part of the sky. And yet these stars are orbiting, in 20 years, they're orbiting thousands of AU, which is thousands of times the Earth's orbit around the sun. They're moving really, really fast. Okay? And that motion, that quick motion, which is about 5,000 kilometers per second, it's about 170 times faster than the Earth orbits the sun. Okay? And the reason why they're orbiting at this great speed, even though they're much farther away from the sun than the Earth is from it, is because there's a big black hole there. Okay? And that black hole we can just measure from really just Kepler's laws. You can measure the mass enclosed in the orbit, and it's 4 million solar masses, 4 million times the mass of the sun. Okay? So this is the supermassive, we call these black holes supermassive black holes at the center of our galaxy. But surprisingly, the Milky Way wasn't the first place that we found these kind of black holes. This paper in 1963 was actually the first time that we really could tell that these supermassive black holes must exist. And it was an observation where the moon had occulted this radio source, and they were able to determine its position really precisely. And they took a spectrum of it, and they were able to measure the Doppler shift of emission lines from this object, and found that they were shifted by 16% in their wavelength. Okay, they were traveling effectively at 16% the speed of light away from us. And as many of you know, the universe is expanding. I think hopefully all of you know the universe is expanding. And that means that this object was extremely distant. At the time, it was the second most distant object known in the universe. And yet, it was one of the brightest radio sources in the sky. And that meant that it must have incredible luminosity. This object is something like 100 times more luminous than our entire galaxy. Okay? So this object is called a quasar. This is what we think is going on, is that material gets dumped onto one of these supermassive black holes. And that is the most efficient way of turning mass into energy of anything we know in the universe. Something like 10% of the rest mass of material that falls into a black hole first gets illuminated or escapes as energy. Okay? And so that's way more efficient than nuclear fusion. And so these objects can be incredibly bright. And so they form point sources in the sky. They just look like stars. And yet, if we subtract off this point source, we can see that there's this fuzzy blob around it. And that fuzzy blob is a galaxy. So this thing is living just like in our Milky Way. This black hole is sitting at the center of a galaxy. Okay? And this generically is true. These quasars live in galaxies. And people realize that if we count up the number of quasars far away, that's pretty equivalent to the number of galaxies nearby. And the argument's a little more complicated than this. It involves trying to find the mass density based on how much luminosity is in the quasars. But roughly speaking, we think that basically every big galaxy, based on the observations of quasars, that every big galaxy should have a supermassive black hole at its center. And in the distant past, it seems like these black holes were growing a lot more efficiently than they do today. And so we see these quasars. And today, we expect them just to be like the one in our Milky Way, just a little maybe fuzzy radio source, faint radio source. So people, of course, wanted to test this idea. And that meant trying to measure black holes at the centers of galaxies other than the one in the Milky Way. Okay? And that's hard because unlike in the Milky Way, once we get far away, we can't see individual stars anymore. So here is this is a Hubble Space Telescope image of the center of the Andromeda galaxy. So it's the highest resolution image we can get. And in every single pixel in this image, there's hundreds of thousands of stars. Because this object is so much more distant, you're compressing all of those stars into a very small area on the sky. So if we want to measure black holes in these systems, we have to take the collected light of lots of stars and examine their motions. The same way we did in our Milky Way, the faster things are moving around, the more mass must be there, and we can infer the presence of black holes. And so that's if you take the light along the slit, you pass it through a grating or a prism, this is the resulting image. This is just from the red part of the spectrum. And you can see that there's these dark bands. These are absorption lines due to calcium atoms in the atmospheres of stars in Andromeda. And if you notice, along this direction is different positions along the galaxy. And the center of the galaxy is right here. So you'll notice, if you look carefully, that these dark lines don't just continue straight through the center of the galaxy. There's a little S shape there. And if you look really carefully, you can notice that it's blurrier right at the center than it is anywhere else. The lines don't look as sharp. Okay? And that is because of the motions of the stars, right? The Doppler shift of the stars. Here, the stars on this side of the galaxy, the stars are coming towards us. They're blue shifted. On the other side, they're going away from us. They're red shifted. And right at the center, there's stars both being blue shifted and red shifted. And so the line gets blurrier, gets shallower and wider. Okay, and we call that the velocity dispersion of the galaxy is very high right at the center. Okay, so that's the basic measurement that we need to make to infer a black hole. And from that measurement, we found that the black hole in Andromeda was more than 20 times bigger than the one in the Milky Way. Okay, so it was 140 million solar masses, so enormous. Okay, and we've done this now in about 100 galaxies. We've measured the motions of the stars near the center of the galaxy, and I'll talk a little bit more about how we tease out the exact black hole mass. But here is a plot that has been made that's very famous in astronomy. It's a plot of the black hole mass versus the overall velocity dispersion of the galaxy. And what this measures is actually the overall gravitational potential of the galaxy. So it's basically measuring the mass of the galaxy. And this is measuring the black hole mass. And it turns out that the black hole mass is only much less than 1% of the mass of a typical galaxy. And so there's really no reason why this should correlate with this. Right? It's just a tiny fraction of the galaxy, and yet there's some really fairly strong correlation between these two things. Okay, and this correlation is called the M sigma relationship because the velocity dispersion is usually denoted as sigma. And it's given rise to a lot of ideas of how galaxy formation must be tied to the formation of black holes. And it's rooted in this idea that quasars are incredibly efficient ways of turning mass into energy. And so that means at that point, the galaxy is way more luminous than it is at any other time. And that can create feedback effects which tie the formation of the gas in the galaxy to the formation of the black hole. And essentially, the black hole can regulate how many stars form in the galaxy. So every time you take a galaxy, you dump gas on it. Some of that gas goes into making stars. Some of it falls on the black hole, and the black hole blows away the gas, and you regulate the amount of stars. And that's how you get this correlation. That's the kind of widely accepted idea now. But something I want you to notice about this plot is that the Milky Way is in the bottom left corner of it. Okay? And that means it's one of the least massive galaxies and one of the least massive black holes that we've measured. Okay? And that's weird because, in fact, we know that most galaxies are less massive than the Milky Way. So for every Milky Way mass galaxy, there's a dozen that are 100 times less massive than the Milky Way. Okay? And so there should be potentially lots of black holes in these low mass galaxies. Okay? And that's the question that I've been working on, is trying to find black holes in low mass galaxies. And I'll talk a little bit about why that's interesting and what we know so far. So, on this question of whether low mass galaxies do they have these central black holes like the ones we found in more massive galaxies? So we have a few galaxies that are in this range, like 1 to 10% the mass of the Milky Way. There's 3 in our very immediate environment. Okay, the galaxy M33 is one example of those, and only one of those 3 galaxies is known to have a black hole, and the other 2 have pretty strong upper limits of about 10,000 solar masses on the mass of their black holes. Okay, so one of them has a couple million solar mass black hole. The other 2 have no detectable black hole. And so that led people to believe that maybe these low mass galaxies just don't have black holes in them. At the same time, we can also hope to find kind of examples of quasars, but in small galaxies. And we call those active galactic nuclei. And what we find is that just a fraction of a percent of all galaxies, these small galaxies, have these active galactic nuclei. So clearly they exist in these galaxies. The black holes exist in the galaxies, but we don't know how common they are. And there's really no evidence for galaxies that are more than about 50 or so times less massive than the Milky Way. There's no evidence for black holes in those galaxies at all. So this plot here shows the stellar mass of the galaxy. So it's in log space. So the Milky Way is here. These things are 10 to the 9 solar mass galaxies. And what you can see here is one of the best sets of observations of galaxies as a function of stellar mass, looking for X-ray sources at the centers of galaxies. And X-rays are a good way of probing even if just a little material is falling onto the black hole, you can sometimes detect that in X-rays. And so you can see that here, by the time you get to Milky Way mass, something like 80% have detectable X-ray sources at their center. But that drops as you get to lower masses. And here's kind of a model predicting how common black holes would be in those galaxies in order to produce these observations. Okay, so it's very uncertain, but below at this kind of 10 to the 9 solar masses, the range could be that all of the galaxies have black holes, or just a third of them could have black holes. Okay. So why is this question interesting? Why do we care if these galaxies have black holes? Well, I mean, the first thing is just that they're the most abundant galaxies in the universe, so if there'd be a lot of black holes by number if that were the case. But there's other things that make this an interesting question. One is that we don't know how these supermassive black holes formed. Okay, so we know about that we have these kind of different kind of black holes, stellar mass black holes. They form when supernovas blow up. And they leave behind a neutron star or black hole at their center. But these supermassive black holes, we don't know when they formed, how they formed. We know that they formed early on in the universe, and because we see quasars at very, very high redshifts, or very early on in the universe. But we don't really know what mechanism formed them. And there's been theoretical arguments for how they were formed, but it's an extremely hard thing to simulate in a kind of realistic way. So there's kind of different scenarios. One is that these seeds that formed these initial black holes at the centers of galaxies were really abundant. And they were common in the early universe. They were, in fact, this mechanism is thought to be that just the very first stars that formed were extra big, and they left behind extra big black holes. So it's basically the same thing as the black holes that we know about in our galaxy, the stellar mass black holes, same mechanism. And that would result in, we expect these early stars to form in basically every galaxy. And therefore, we'd expect even low mass galaxies to have black holes at their centers. Okay? On the other hand, if these things were formed in some more rare mechanism, and the mechanism here is that you directly collapse something like 10 to the 5 solar masses of material into a black hole in the early universe. And that produces much bigger black holes, but in many fewer cases. And so in that case, you would expect these low mass galaxies not to have black holes in them. And so probing at these masses well below the Milky Way's mass is one way of distinguishing, really the only observable way of distinguishing this black hole seed formation mechanism. Although, hopefully with JWST, there's hopes that we'll directly observe them forming in the early universe. Another interesting question is, we know from LIGO that black holes exist up to 62 solar masses. So the black hole that was observed in the very first LIGO event that was reported was the merger of two 30-some solar mass black holes. The end result was 62 solar masses. And it's the most massive black hole that we know of that's a stellar mass black hole in the universe. Okay? At the same time, we know these supermassive black holes exist. And they're like 1 million solar masses and up. Okay? So there's 4 missing orders of magnitude. That's crazy. And there's a lot of controversy in those 4 missing orders of magnitude. So people have claimed in the centers of globular clusters in our Milky Way, which are dense star clusters floating around our Milky Way, they've claimed that there's something like 10,000 solar mass black holes at their centers based on the motions of stars. And those same other people will observe those same objects and say, no, you don't know what you're talking about. There's no black hole there. So it's been extremely controversial. There's been a lot of back and forth on this. And I've been involved in a project looking for radio emission. I mentioned to you that the black hole at the center of our Milky Way is a radio source. And we would expect any black hole to have radio emission at some low level based on just the fact that space isn't empty, right? There's stars around, they lose mass, there's stellar winds, and those stellar winds will fall onto the black hole. And so we can place, by taking deep radio images, we can place upper limits on the black hole masses. And the upper limits we find are an order of magnitude below the claimed black hole masses in these objects. So these pink ones are all objects for which there's been claimed dynamical detections of black holes, but we don't see any radio sources that are consistent with those black holes. There is one object in the universe which has this really totally unmemorable name. that seems to be a rapidly accreting intermediate mass black hole. And it's really, really bright. It's called what's called a HLX stands for hyperluminous X-ray source. And it's the brightest X-ray source that we know of that's not in the center of a galaxy. Okay, and it's our best example of an intermediate mass black hole. And it's in a galaxy 100 megaparsecs away, so very far away from us. So there's one example. So finally, this M sigma relationship, there's a lot of leverage by going to lower masses on understanding the physics that's going into creating this relationship. And so, we'd really like to know, for constraining this relationship, what's going on down here. Yeah?
I just have to ask, this is kind of a geeky question, but the Milky Way point on this graph
Yes.
has the largest horizontal error bar.
Yes.
So
it's really hard to measure something when you're sitting in
live here.
Yeah, so it's really hard to measure something when you're living in the center of it. So, if we try measuring what the properties of our galaxy are, especially towards the center of the galaxy, we have to look through a lot of dust extinction. So there's something like only 1 out of every 10 to the 10 photons that's emitted from the center of our galaxy at optical wavelengths makes it to us. Okay, so that's why it's really hard to figure it out. Yeah. Okay, so my goal is to find low mass black holes, and that's a tricky thing to do because in order to find the low mass black holes, they don't influence as many stars, right? If their mass is lower, their dynamical effect is going to be smaller on the stars that surround them. And so we really need the highest possible resolution observations. And it turns out that the best technique for doing this is something called adaptive optics. So when you go out at night and you see the stars twinkling, right, that's because there's turbulence in our atmosphere, and the refractive indices of different temperature cells along the line of sight causes the light to bend and dance around. And that means the little twinkling that you're seeing on the sky is the star kind of moving around, and that's causing this twinkling, right? And so we hate that. We don't like twinkling at all, and we want to remove it. And the way we do that is, in this case, this is the Gemini telescope in Hawaii that I use for a lot of my work. This orange thing coming out the dome there is a laser. And that laser hits into sodium atoms in the ionosphere, makes a little bright star at that location. And then that light we can observe and see how it's being distorted and try undoing it. So we take a mirror and every time the star moves to the left, we move it back. Okay, so that's adaptive optics. And it allows us essentially to get diffraction-limited images, something like the Hubble Space Telescope gets, but with a much bigger telescope. The Hubble Space Telescope's 2.5 meters. This telescope is 8 meters in diameter. And so, to make these black hole mass measurements, we essentially are looking for a combination of measuring the stellar motions. So the motions of the stars, and you'll see a lot of maps like this. This is showing the velocity dispersion as a function of position in this object. And you can see this red dot at the center is exactly like that blurry section of the image that I showed you in Andromeda. It's telling us the stars are moving quickly there. And that's telling us how much mass is there. But then we also, in general, we need to take into account the mass of the stars too. So some of this motion is just due to the stars. So we take a model, and we actually use the Hubble Space Telescope for that. We take Hubble Space Telescope images of the galaxy, and that tells us how the mass is distributed. And if there's a mismatch between how the mass is distributed and what we infer from the mass from the motions of the stars, then that can tell us there's a black hole. Actually, if there's, if this red dot at the center, here, the fast motions are the center, don't come from stars, then they must come from something else, and we infer that there's a black hole there. But in general, it's actually pretty hard to measure the stellar mass profiles. And that's because the light doesn't always trace the mass very nicely. And what you're seeing here is actually a color image. So it's the ratio of fluxes in 2 different wavelengths. And you can see that in this the center of this galaxy, there's variations in the colors of the stars. And those variations in the colors of stars are telling us that there's different ages of stars, and those different age of stars have different masses associated with each flux, all the flux that we get. So what we refer to as the mass to light ratio changes. And in particular, young stars are really, really bright for every unit mass that they have, whereas older stars are fainter per unit mass. Okay? And it turns out that, and this can happen also not just from older and younger stars, but also if there's dust along our line of sight that blocks some of the light out. So all of these things make things a problem, and they're a particular problem in these low mass galaxies where we want to do these measurements. So the sample that I'm going to be talking about first here is this sample of nearby galaxies. So this is the distance in megaparsecs, so that's roughly millions of light years. So this is like 10 million light years about here. These are very nearby objects, okay? These are in the nearest 100 galaxies, say. And this is versus their luminosity, and these things typically have luminosities and masses, something like 10 to the 9 solar masses or so. And I'm going to be talking about these 6 objects that are starred here. So the first one is this galaxy. It's NGC 4395. It's a very pretty spiral galaxy. And it's the first galaxy that doesn't have one of these. Typically, galaxies are spirals and ellipticals, and the spirals have these little elliptical-like components at their centers that we call bulges. This galaxy has no bulge, and it's interesting because we often correlate the black hole masses with the bulges. And so this is kind of an exceptional galaxy. It was found quite a while ago to have this basically like a little mini quasar at the center of it. And people can use the properties of the light. They actually use the time lags of the emission from that quasars to infer the black hole mass in kind of an indirect method. You essentially take the width of the object, of the line to measure how fast they're going around, and then the time delay gives you a physical time scale, and you're able to measure a gravitational mass that way. So we actually are trying to measure a direct gravitational mass, and here what we have is, in our observations, we have an emission line from molecular hydrogen gas. And we're able to trace, this is its radial velocity, so this side is coming towards you, that side's going away from you. And then this is the dispersion, how fast this gas is moving along the line of sight. And you can see that it's what we would say very cold. It's not moving very much along the line of sight. And it's in pretty nice rotation here. And so we're able to use that rotation and assume it's on Keplerian orbits to constrain the black hole mass. And you're going to see a bunch of plots like this. This is the mass in stars on the y-axis versus the black hole mass here. And these are our constraints from our modeling. And so basically, you can see that there's this kind of degeneracy between having more mass in a black hole versus more mass in stars. And we see that typically, because you can imagine, if you don't know that there's a black hole there at all, you could either put the mass that's causing the stars to move around in the black hole or in the stars. Okay? And here's the previous measurements. And so there was an order of magnitude difference between them, and we're able to very clearly resolve that issue with our measurements. Here's another object. This galaxy has a great common name called Mirac's Ghost. It's right next to the star called Mirac. And it also has some evidence for being a black hole that is accreting a little bit of material, that has a little bit of material falling onto it. I had done some work on this in 2010, and I had 2 different tracers to measure the motions of objects around the black hole, and they gave 2 different answers. So we were trying to, so recently we've kind of re-examined this data, and we re-examined it in the context of having better handle on the mass that is there. And we really think that there really is a black hole in this object. We can see lots of signatures of the mass falling onto the black hole, but we don't know what its mass is. And so what we were trying to do, this was that object I was showing you that color map of earlier. And what we want to do is we want to take this color map and figure out from the colors what is the mass of the stars at that location. So in every pixel in this map, we want to know how much mass of stars is there. And then we can deproject it and figure out what the 3D mass profile is like. And to do that, we got Hubble Space Telescope spectroscopy along this white line. So we were able to get, this is this optical spectra, so this is at kind of green and blue wavelengths. And there's a lot of, you can see there's a lot of wiggles in it, and all those wiggles are real features, okay? And those real features tell us a lot about the ages of stars that are present at that location. And so what we're able to do is we're able to predict how much mass there is per unit light as a function of this color based on this Hubble spectroscopy. And so we were able to construct this kind of better mass model at the center of this galaxy, and that allows us to get better constraints, more reliable constraints on the black hole mass. So here is a plot that shows how fast the stars are moving around on this axis versus the distance from the center of the galaxy. And you can see there is a little bit of a rise towards the center of the galaxy. But the black line here is a model with no black hole. Okay, so essentially this black line is showing us that the data is consistent with there not being a black hole here at all. Okay, and this top line here would be if there was 1 million solar mass black holes. So you can see that that's very clearly excluded by the data. And so what we can do is we can get an upper limit on the black hole here, and we actually know there's a black hole here. So this is actually the lowest mass central black hole that we know of in a galaxy. It's below 2 times 10 to the 5 solar masses. And this is that same plot of mass of stars versus the black hole mass. Okay. So we've done this. My student Yu Nguyen has done this. He's for 4 more galaxies. These are all something like 50 times less massive than the Milky Way, or 10 to 50 times less massive than the Milky Way. And we find that in that mass range, we find black holes in 4 of the 5 objects that we've studied. Okay, so here is a galaxy that the black hole was already known. It's the Messier 32. It's a satellite of the Andromeda Galaxy. And here are 2 more that we found for the first time. And you can see all of these plots are how heavy the stars are, and it's actually how heavy they are relative to what we expected based on our models. So 1 is like exactly our models, and they're 10 or 20% variation from that. And then the black hole mass is on the x-axis, and anytime the 3 sigma, this is 1, 2, and 3 sigma contours, and anytime these 1, 2, and 3 sigma contours don't extend all the way to the left-hand side of the plot, that's a detection of a black hole. Okay, so in this galaxy, we didn't detect a black hole. We just got an upper limit. But in these 2 galaxies, we did. Okay, and so we find that 4 of the 5 galaxies that we've studied here have black holes, and 3 have black holes that are below this kind of million solar mass mark that previously we didn't know about black holes that were like that. And if we plot them on here's the M sigma relationship that I showed you earlier. And this is, instead of being the velocity dispersion, this is against the mass, the bulge component of the galaxy. And you can see that they don't follow on this relationship, they don't follow the correlation seen for higher mass galaxies. They seem to be below the relationship. Whereas on this M sigma relationship, they do seem to follow maybe even above the extension of the correlation to higher masses. Okay. So this is the first part of the talk, and I'm going to switch gears a little bit. But I think the thing that we've learned is that there really are black holes down here, and we're already starting to get constraints that suggest that maybe this more common seed formation mechanism was what was responsible for forming these black holes. Okay, so now we get back to the mystery image. Okay, this is a galaxy known as Messier 60. So it's another nearby bright galaxy. And it's actually one of the biggest galaxies we know of in the local universe. And so you might be confused because I was talking about small galaxies, right? Not big galaxies. This galaxy does have a black hole at the center of it, and it's one of the biggest ones we know about. It's 4.5 billion times the mass of the sun. Okay? It's like even hard for me, it's inconceivable, right? This galaxy is a galaxy that's probably falling into this galaxy, and we don't know about whether it has a black hole in it or not. But what I'm going to be talking to you today about is this little dot down here, okay? that little dot, it turns out, has a 20 million solar mass black hole in it. Okay, so there's the little galaxy. And what we call this kind of galaxy is an ultra-compact dwarf galaxy. Okay, so that little fuzzy blob, this is the Hubble Space Telescope image. It's the best image we could get of it. But if we were able to go up close to it, it would be hundreds of millions of stars packed into a tiny area less than 100 light years across. Okay, so one of the densest objects that we know of in the universe, and we call this thing an ultra-compact dwarf galaxy. This is a globular cluster in our own Milky Way galaxy that's a very dense globular cluster. And this is a Hubble Space Telescope image. So it gives you kind of a sense of what we would be looking at if we were able to get much closer. And because I like to show some data, here is what the actual data looks like of the motions of stars at the center of the object and further out. And what you'll notice here is at the center, the lines are broader. That's equivalent to blurrier in that image that I showed you. The velocity dispersion is higher at the center. It's about 100 kilometers per second. Whereas further out, it drops to about 50 kilometers per second. And so we can make a map by taking, we use integral field spectroscopy, so we get measurements of the whole object. We get spectra in every pixel. And that allows us to make Doppler shift measurements over this whole region. Okay, and what you're seeing here is the motions of stars in that ultra-compact dwarf. And you can see here that again, this thing is rotating. Okay, so this side is coming towards us, that side's going away from us. And right at the center, this is the image I used earlier, there's a red dot, which is suggesting that the velocity dispersion is very high right at the center. You might recall, with Andromeda, that was the signature of the black hole, that high velocity dispersion. And as soon as I saw this, like a day after I got this data, I knew that we had a detection, because this is a really extreme peak in the center. And kind of to give you a sense of what that looks like, here is the velocity dispersion plotted against the center, the distance from the center of the galaxy. And this dashed line is what we would expect if there was no black hole in this object. Okay? And so you can see that it looks nothing like these x's, which are our data, and that in order to replicate those x's, this upturn at the center, we need to have a big black hole there. And it's about 20 million times the mass of the sun. Okay? This is the modeling method that we use we use different modeling methods, but one of them is a kind of an orbital integration model. So you basically create a potential, and then you figure out all the possible orbits in that potential, and you weight them to match your data. And that's kind of considered the gold standard of black hole mass measurements. And this is the weight of the stars versus the black hole mass. And these are our 1, 2, and 3 sigma contours here. And so you can see the black hole mass is constrained to be well above, or above 10 million solar masses. And no black hole is very strongly excluded in these models. And they're extremely flexible, so this is really a strong statement that there is very likely to be a black hole here. So this object is really weird. It's the lowest mass system known to have a supermassive black hole. Okay? The total mass of the system is only 120 million solar masses, and yet it has a 20 million solar mass black hole sitting at the center of it. That's 15% of the object is in the black hole. Okay? It's the highest mass fraction that we know about. And for reference to the Milky Way, its black hole mass is 5 times higher than the Milky Way's mass, and this mass fraction is way, way higher. So in the Milky Way, the black hole is only 0.01% of the total mass of the galaxy. But in this object, it's 15%. Okay, so very weird object, but we think we have an explanation for this, which is that these ultra-compact dwarf galaxies aren't just living anywhere in space. They live preferentially near big galaxies. And what we think is that galaxies like this one, if they fall in, their outer layers can be stripped away. And I have a kind of movie here to show that this is a 10 to the 10, typical 10 to the 10 solar mass galaxy. And we've thrown it into something that's a simulation of a potential that's reflective of what we think this galaxy's gravitational potential should be. And if it passes very close to the center, the tidal forces from the galaxy, from the big galaxy, strip the outer layers off of the little galaxy. And so you get all of the galaxy, through repeated passages, the outer layers keep getting torn away. They form these great little umbrella structures, which probably dissipate over time. So if this happened a long time ago, we wouldn't expect to see it. And through the magic of computer simulations, it ended up exactly at the right location, right? But we can do a realistic simulation that shows that you really can take a normal galaxy and strip away everything except the core of that galaxy, and you're left behind with something that looks like this ultra-compact dwarf galaxy. Okay, so it's like that picture I showed you at the beginning with the Milky Way. There was that bright clump of stars at the center. It's like we took all of the Milky Way, stripped everything else off, and only had that clump of stars plus the black hole. Okay, so that, it's pretty exciting, but the most exciting thing about this is related to some kind of a mystery about these ultra-compact dwarf galaxies that already existed when we made our measurements, which was that when we compared how much they weighed by measuring the overall motions along our line of sight, the velocity dispersions, we were able to convert that into a dynamical mass estimate, and then compare that to how much mass we thought should be there based on the starlight that was there. We found that there was too much mass there in these objects. So down here, so what this is showing is the mass of these are globular clusters and ultra-compact dwarfs, and this is the ratio of how much we measured the weight to be of the galaxy versus its estimate from the starlight. Okay? And what you can see is that, in general, the one here is the maximum that we would expect for these objects to have. And you can see that in general, these ultra-compact dwarf galaxies were too heavy. Okay? And the proposal, before we made our observations, one of my collaborators, Stefan Miski, made the suggestion that maybe the reason why all these things are too big is because they have these high mass fraction black holes. And it's amplifying the motions of the stars, and by taking models that assume that there's no black hole there, we're getting too heavy of an object. And this was borne out with this object. It was just a little over this one line, but after we subtracted out the black hole, it actually was about 70% of the maximum value. Okay? So that suggests that maybe all of these objects here have, all of these massive ultra-compact dwarf galaxies have black holes in them. Okay? And that is exciting for a lot of reasons. We think this stripping process happens a lot. Galaxies in the universe interact with each other a lot, and big galaxies have lots of small galaxies that fall into them. And so this is observations of the nearest big city of galaxies, the Virgo cluster, to our own. And if you include this red histogram, shows just the brightness, the luminosity function, so how many galaxies at a different brightnesses there are. And if you just include the galaxies, but if you take some recipe for figuring out how big a galaxy did these UCDs come from, and include those progenitors that may have gotten stripped away, there's actually a factor of a couple more of these progenitors. So for every present-day galaxy, there's several galaxies that have been stripped in the past. And that would suggest potentially that there could be as many black holes in these stripped galaxies as there are in present-day galaxies. And in our local group, in the Milky Way and Andromeda, there are these clusters at the centers of galaxies, nuclear star clusters, and there's 6 of those that all have masses of 1.4 million solar masses or more. And there's 19 globular clusters that have masses in that range, and several of them have been proposed to be previously stripped galaxies for various reasons. So this could be common in many environments. So we went to get more data, and we found that this object isn't unique. So here's work from Chris Ahn, my grad student, another grad student who's finishing this year. This is around another galaxy in the Virgo star cluster and galaxy cluster. And this little dot here is that UCD. And this is a Hubble Space Telescope image of that. And when we take our data, we find again that there's a big peak in the central dispersion. And it's higher than we'd expect if there was no black hole. And in this case, the black hole mass was much lower, 4 million times the mass of the sun, And the stellar mass was very similar to the stellar mass of the nuclear star cluster of our galaxy. So this thing is very much like what we'd expect if you stripped away our Milky Way's mass. Okay, very similar. Here's another object. Same story, 6 million solar masses, 35 million stellar masses. So these things are both high mass fraction, over 10% of their mass is in their black holes. And then it turns out around this galaxy there's two of these objects. This one is super bright. It's the brightest UCD we know of. And we have really beautiful data on this one as well that my student Chris is working on for his final paper. And you can see here's the data, and here's our best fit black hole model. And even our best fit black hole model kind of underestimates the little peak at the center. But this object doesn't have nearly the mass of the black hole. It's only about 2% of the mass. It's just at the kind of limit at which we could detect even with this really good data. And so here it's a few million solar mass object in 100 million solar mass UCD. Okay, so to summarize, we find this is the same plot I showed earlier, which showed the globular clusters and ultra-compact dwarfs, and how overweight they were. Okay, and what you're seeing with all these stars is objects that the original estimates for how heavy they were, and then the estimates after we corrected for removing the black hole. And what you can see is that in every case they fall below this maximum mass line that we would expect. And there's two lower mass objects that we've studied. My postdoc Karina Vogel just submitted a paper on this. And these two objects don't seem to have black holes. We only get upper limits on them, but they're right on this kind of one line, so we don't necessarily expect that they would. So this is an example of that data, and here you can see the velocity dispersion is flat rather than being inclined, and in fact it doesn't even fit very well to our best fit models, and this may be related to problems with our relatively limited imaging. Okay, I think I'm going to stop there and just conclude. So we can dynamically detect black holes in these sub-Milky Way mass galaxies, and their demographics can tell us about the formation of massive black holes. And these stripped galaxy nuclei do seem to host black holes, and there might be a lot of these, and they could actually help us probe this same scenario of these low-mass galaxies. A lot of these low-mass galaxies may have been stripped, and it turns out it's easier to find the black holes in these objects than it is in the centers of galaxies. Thanks. Yeah.
I'll let you.
Okay.
With your, I think, NGC 404
Yeah.
data, there was you had a plot where you had the what you would expect for no black hole versus a very massive black hole, and your data seemed to have a kind of a hump.
Yep.
Yes, that one. That's right there.
Yes.
An explanation for that?
Yeah, I think that
Pretty small.
we're forcing our model to be our model has to be axisymmetric, okay, and we fit smooth axisymmetric components to the overall image, but in fact there's residuals in that fit, and so it's probably true that that our mass model isn't perfect still, even though we've made our efforts to improve it. And that's related to why we're getting these observations. The other thing that could be happening is there's dust in this system, and the dust can not only affect our observations of the mass model, but also where we're getting the motions of the stars from. So you can imagine if there was a screen of dust, you'd only observe the stars in front of it and not behind it. And so that could affect what the measurement of this velocity of our stars a little bit. So these are all uncertainties that are particularly problematic when you have these really complicated situations. Yeah.
And it was about just a general sort of question about, say, at our galactic center, when you have a star orbiting as close as they do.
Yeah.
Are there effects on the structure of the stars from tidal forces?
Yeah.
Okay,
So I just went to a conference that was all about what are called tidal disruption events. And so occasionally a star will be on like a plunging orbit, and it'll come so close to the black hole that the tidal forces will be stronger than the gravitational force of the star itself, and it'll unbind the star. Okay, and when that happens, you get basically like something like a supernova explosion, but a lot of the energy is actually coming from all of a sudden you're dumping material onto a black hole that previously didn't have any material on it. And so it's like almost like lighting up one of these quasars instantaneously. And so there's this kind of some very confusing sets of signatures of these objects. There's, some of them have X-ray emissions, some of them have UV emissions, some of them have optical emission, but we've identified about a dozen good candidates for these tidal disruption events. And that's a really exciting thing going forward because they allow they should really probe high mass and low mass black holes equally. And so and we're going to have with the Large Synoptic Survey Telescope, which is a new telescope that's going to be coming online in about a few years, there's going to be we're expected to detect 100 of these every year. So we're going to really start being able to do like demographics of the black hole population from them. So it's really interesting. Yeah, good question.
One follow-up to that is
Okay.
in your stripping events,
Yeah.
are those, presumably that's the proximity of the black hole that's doing the stripping?
Well, so I mean, even in that galaxy, you have to get the object to pass within about 1 kiloparsec, or 3,000 light years of the center of the galaxy, and within that radius, the black hole at the center of the big galaxy doesn't actually dominate the total mass. There's actually more stars there, so it's actually the stellar mass of the galaxy that's creating that tidal force. Yeah.
So near the beginning, it looked like you're mostly focusing on elliptical and spiral type galaxies.
Yeah.
Are there any sort of correlation whether you would expect to see one of these massive black holes in a particular type of galaxy?
Yeah. So if we go back to this the M sigma relationship plot I showed you earlier, here the red dots are elliptical galaxies and the blue dots are spiral galaxies. Okay, and if you can imagine subtracting off all the red dots from here and leaving only behind the blue dots, you can see there really isn't much evidence for much of a correlation there. Here's a galaxy that's at the same velocity dispersion as M31, but its black hole is 2 orders of magnitude less. Okay, so there's this huge spread in black hole masses in these spiral galaxies, and so this picture of this feedback mechanism seems to maybe only hold for these elliptical galaxies, and that actually kind of comports with one of the scenarios that we think is related to this feedback mechanism, which is that it happens when galaxies merge, that a lot of gas gets dumped onto the galaxy, they grow very rapidly, and they feed their black holes at the same time. And the biggest galaxies in the universe are all elliptical galaxies, and those result from those are the end product of these mergers of galaxies. So yeah, so the answer is yes, we expect these elliptical galaxies in general should have more significant black holes, and that they should follow this relationship tighter. And in these spiral galaxies, it's a little less clear what's going on, and that's actually something that we'd really like to know is, can we find black holes in little ellipticals and spirals? Are they different in masses? And that's something we're still on the edge of not, we don't really have the data yet. Yeah. Yeah.
So I'm not sure if I got this right, but you seem to show there are two ideas of how to make really big black holes and how really small black holes go into really big ones.
Uh-huh.
And your data seem to, at least the way I understood it, maybe totally wrong,
Yeah.
that there seems to be one formation process rather than two different ones.
Yeah.
But then how come that we don't see the size of these 4 orders of magnitude in between?
Yeah, so it's a great question. It makes me, so what I would say is, yes, it seems like that the low mass mechanism must have taken place. It doesn't mean that the high mass one didn't also take place, right? You could have both of them. It's kind of simplification to say one or the other. But the low mass mechanism must be taking place, I think, would be if a large fraction of these low mass galaxies have black holes. And I would say 4 out of 5 is, pretty small numbers to make big conclusions on, but there's other studies which also suggest that that there might be a high mass fraction. So then why, you're right, it's very uncomfortable with then why don't we see these objects? And I think it's probably a selection effect in the sense that the lower mass the black hole is, the less luminous any kind of, if a gas falls onto it, that the luminosity is proportional to the black hole mass. And so these big black holes, you see them much more easily than you do the little ones. And so I think that's really, I mean, that's the only way to really reconcile those problems. Yeah.
That's hard with 4 as a magnitude.
Yeah, it's really amazing. Yeah, I agree. I think it's, it's definitely still an outstanding problem. And I think there's actually lots of ways of tackling that problem. In fact, the gravitational waves may be our best answer for that because, especially if LISA, the other gravitational wave, the space-based gravitational wave thing happens, we will, if these intermediate mass black holes merge within anywhere in the universe, we'll detect them. So, yeah. Yeah.
Something I kind of missed, when you add the low mass galaxies, you said they seem to follow or slightly above the n-sigma relationship,
Yeah,
but when you plotted black hole mass versus bulge mass,
that's right.
didn't, and I missed how you were getting bulge mass apart from sigma. Is that just from?
Yeah, so the sigma is a measurement of the velocity dispersion of the central region of the galaxy, and the bulge mass is is done by decomposing the galaxy into a bulge and a disk component, and taking just the bulge component. So, and it's probably because that the bulge, there's a kind of the Faber-Jackson relationship is just this like relationship between bulge mass and the sigma probably changes at lower masses. Yeah. All right.
Any more questions? Okay, if not, let's please thank our speaker again.